So good morning and welcome to the second day of this conference. So I would like to present Pietro de Lelis from Naples. 25 minutes plus questions.
I think you can keep this, yeah. Just in case. Okay, so just the first, just a few words for the students. So in the first slides, there will be supposed to be easier for you because of the lecture that you attended in the last week. Then at some point you need to focus, make a bigger effort to follow. So this presentation will be about a line of research that we are carrying out on the effect of directed many-body interactions on the spontaneous or controlled emergence of synchronization. So apparently this is not working. Okay, I will use this. So in the classical pairwise model of synchronization, you have that individual dynamics described by a vector field f. Then you have an additional term which is related to the interaction of node I with the neighboring nodes, and then you possibly have a further term, a third term, which is a control term, that is related to an additional node, which is called typically in the literature the pinner node or the leader node, which is unidirectionally coupled with a subset of the nodes in the network. So now, as a result of this local interaction, you have synchronization emerging in the network, and be it spontaneous synchronization or be it controlled synchronization, in any case, what the mechanism that underlies the onset of synchronization is this kind of diffusive-like mechanism taking place in the network. So the underlying assumption is then that this diffusion takes place between pairs of agents. So the underlying assumption is that you have pairwise interaction. Well, we are at the workshop on higher order interaction. We know that interaction can also be higher order. I don't need to motivate that. This has been done very clearly by Stefano yesterday. And but what I would like to focus your attention on is that the need for having higher order interaction also comes from control. And in particular for control when you have limitations on the sensing. And why is that? Because an underlying assumption when you consider the pinning control strategy is that the pinner is able to individually measure the state of the nodes where he injects the control signal. Because you can see here there is a feedback control action which depends on the difference between the state of the pinner and the state of node 1. So every time we draw a directed edge, we mean that we are able to measure the state of this node. Okay, but in general, this is not always true, and sometimes in many control applications, you have some limitation on sensing that, and what you have at your disposal is only an aggregated measurement of the state of a group of nodes. For instance, you might be able to know the average state of this pair of nodes here. Okay, so I would like to mention an example in system biology where sometimes the feedback mechanism rely on the fluorescence of the cell. So if your resolution is not at the level of a single cell, you cannot measure the state of a single node. So to study these cases, you cannot draw any more directed edges, but you should consider directed hyperedges. Now, what kind of formalism? So there are several ways to introduce directionality in hyperedges. The formalism that we choose that was suitable for our purpose was to consider a definition that comes from a paper in Discrete Applied Mathematics in 1993, where the hyperedge is defined as two order sets, the set of tails and the set of heads. Now, the tails are the nodes that send the signal, so in this case, node 1, and the heads are the nodes that receive the signal. And the signal itself will be a function of the state of all the nodes that are involved in that hyperedge, that belong to that hyperedge. So you have a natural generalization of the concept of the standard equation when you consider directed interaction. So you pass from this model, where the pinner is a node that has only outgoing edges, because it's a node that influences but is not influenced by the rest of the network. And then you pass instead to another more general model in which the pinner is the only tail of the hyperedges it belongs to. So the tail is the node that is sending the signal to the heads, which are the nodes where the signal is being sent. That receive the signal. And as you can see here, the fundamental modification here is this generalization of the diffusive mechanism. So in the standard model, you have a function, a nonlinear function, of the difference between the state of node J and state of node I. Here instead you have a nonlinear function of the difference between a convex combination of the state of the tails minus a convex combination of the state of the heads. And fundamentally, this is a synchronization non-invasive coupling protocol, because if G is 0 at 0, this term will disappear when all the nodes have the same state, so when all the nodes are synchronized. Now, how do we study this type of systems? Well, we can study this type of systems, so we have studied this type of systems by means of an association that we were able to make between directed hypergraphs. So instead of using then tensors to describe these directed hypergraphs, we could go back to matrices because we find this association with signed graphs. So basically, we find that instead of studying the hypergraph, we can study a special class of sign graphs, in which the conversion, let's say, is pretty straightforward, because if you take an hyperedge, then you can replace this hyperedge with positive edges from from each tail to each head, and negative edges between the tails, between the heads. So you have also this sort of, that highlights such a kind of repulsion mechanism also being present in this scenario, in this directed scenario. So now this association allowed us to use classical tools for studying a network system, which include Lyapunov methods and the master stability function. And I would like in this first to mention some of the quickly some select results that we have been able to achieve, and then I would like to answer together with you to a specific question related to directed interaction. So let's first focus on the well-assessed results that we have already published, and then I would like to show you something that we are doing right now. So first of all, we have been able to show that something that is prohibited in pairwise interaction can happen in higher order interaction. For instance, those repulsion that you can see from the negative edges make the the topology also responsible for some potential instabilities in the network. And so even in the simple consensus dynamics, which may never be unstable on graphs, you have that possible divergence. And this is because when you consider the Laplacian associated to the sign graph, that Laplacian is not anymore, its eigenvalues may also be negative. So the instabilities may also come from the topology, not only from the individual dynamics. Then we also have been able, using Lyapunov-based approach, to find global sufficient condition for controlling the network to the desired trajectory. And using these conditions, this global condition, we built a control heuristic that sequentially adds hyperedges, the pinning hyperedges to the network until some condition is met. The condition is met, and you can synchronize the network onto the reference trajectory. Here you can see an example of a network of Chua circuit, a simple example with few nodes. And after the application of the control heuristic, you can see that the error norm goes asymptotically to 0. This for all initial conditions. Then we have been studying also local conditions. So, and the local conditions have been derived using the master stability functions. These conditions are necessary for synchronization. And we found some interesting findings. One was that if you increase, so not always increasing the resolution of the measurement is an advantage. So being able to individually measure the state is not always beneficial. So sometimes also an aggregated measurement can be effective. It can even be, under certain circumstances, can even be better than controlling individually each node. So measuring the state individually of each node. Okay, so now this is what we have established so far. Now let's try to make a step forward. And let's try to understand what are the higher order structures that most favor synchronizability or pinning control. So first of all, and how does this structure compare with the pairwise interaction? So are higher order interaction better for synchronizability, worse, the same? And among the higher order structure, are there some structures that are more favorable for synchronization? Well, first of all, we need to agree on what we mean with synchronizability. Yeah. Yeah. First of all, we need to agree what we mean by synchronizability. And I would like to start first with an example to introduce the problem. And then after the example, we try to give a more general answer to the question. So let's consider an example from opinion dynamics. So where you have the individual dynamics described by this function here. Basically, every node is a bistable system. You have the positive equilibrium, you have the positive and negative equilibria that are stable and that correspond to a positive or a negative opinion. Then you have the unstable equilibria at 0, which correspond to a neutral opinion. And then you have this parameter mu I that can be different from node to node and is the level of extremism of the individual. So the higher will be mu I, the more extreme will be the steady state opinion of the individual. Okay, now a possible control problem is to estimate the norm of the steady state opinion mismatch with respect to the reference given by an opinion leader that we can call pinner, we can call influencer, we can call as we like it, and then to estimate this steady state opinion mismatch and design control strategies that minimize such mismatch so that the opinion of all the nodes gets closer to the reference given by the pinner. So how do we do that? Well, to do that we use a Lyapunov-based approach, and in the end what we find is a bound which will depend on the hypergraph topology, the control hyperedges that we choose, so how the leader is connected with the neighbors, and from the coupling and control gains. So now let's keep this coupling and control gain fixed. So at this point, for a given hypergraph topology, this will only depend on the selection of the pinning hyperedges. Now let's consider this example here. So you have, assume that you have 4 communities of 26 nodes each. Then you have a parameter rho that regulates the modularity. So basically, it's the ratio between the inter and intra-community hyperedges. We assume that it's small. And then we keep fixed the number of hyperedges within the total number of hyperedges within communities. Communities 2 and 3 will have the same number of hyperedges, while we'll have another parameter psi, which will be the ratio between the number of hyperedges in community 4 and the number of hyperedges in community 1. So this means that when psi is equal to 1, all the communities are equally dense. For psi smaller than 1, you have that community 1 is the densest and community 4 is the sparsest. Okay? So now what we need to do is we need to assume that the problem that you need to solve is the leader needs to decide which community to try to control to minimize the overall mismatch with the entire network. So it needs to choose among as 4 possible alternatives. Okay, so how do we study this problem? Well, we study it in, first of all, we consider a grid of the parameters rho MC. And then for each pair of the parameter and each choice of the community to control, we randomly generate the hypergraph topology. Then we record we estimate the opinion mismatch and record the choice that minimizes the opinion mismatch, the estimated opinion mismatch. And then we, as a ground truth, we simulate the system and check what is the actual best strategy to minimize the actual bound. And what we find is that for all parameter combination, in at least 96% of the cases, we will get the same choice. So the choice using the bound, our bound, is consistent, is at least in 96% of the cases, always consistent with the actual optimal choice. Okay, so the bound works quite fine. And we can also have a look at what does it mean, what does it mean for with respect to the parameters, what is this optimal choice that you are going to take. So first of all, when the community are have the same density, all the communities have the same density, basically it's the choice is uniform across the community. You don't have any specific reason to prefer one community or the other. So it will depend on the specific extraction of the random topology. But when instead the communities are heterogeneous, you have that you will prefer to the choice of the sparser community. And this is even more prominent, this effect, when you have few inter-community hyperedges. Okay, so this approach looked viable for selecting the optimal topology, but here what you were choosing of the topologies were just the control hyperedges. So everything else was fixed. We were just deciding the control hyperedges. Now let's try to make it a little bit more general. Let's try to generalize what we did for this application. And so, can we compare? So in this application, we had basically individuals that were different from each other, and we were trying to reject these mismatches and bring them together anyway, regardless of their mismatch in extremism in that case. So can we generalize what we did and compare hypergraphs in terms of their ability to reject mismatch in the individual dynamics? So we measure synchronizability as the ability to reject mismatches in the parameters. So the nodes are not anymore identical, are maybe different from each other. So are we able to reject such differences? So that's the idea. And now, well, I would like to stress that this is not a trivial question, and also its answer is non-trivial. Let me make an example. So yesterday we were talking about Kuramoto and the Kuramoto model. Now, on panel A, you can see a pairwise network, and in this, so this pairwise network is let's consider this is the network that you consider for your Kuramoto model. So you consider Kuramoto model with this net, so not all to all, but described by these connections here pairwise. And then instead, in the other panels, you will consider higher order Kuramoto models. And let me show which ones. So this one is the one that was introduced by Stefano yesterday. And you can see the references here to Skardal and Arenas and to Kovalenko and Stefano. And so in this model, in our formalism with heads and tails, so becomes a hypergraphs with only sync hyperedges. So sync hyperedges are hyperedges which have two tails and one head. Okay? So if you write in our formalism, you find all sync hyperedges. So this topology is all sync hyperedges. Then I think Jose was asking if there were also other Kuramoto models in higher order, and there are other type of Kuramoto models for triadic interactions. And in our formalism, this corresponds to what we call source hyperedges. So just one tail and two heads. So now these three models here are all Kuramoto. This is pairwise, these two are higher order. And they share the cardinality of the hyperedge set. So the number of hyperedges is the same. The number and it's the same as the number of edges in this case. And so but when you compute the order parameter, you will see that you will get very different results. So it seems that this is more synchronizable than pairwise interactions, and is more synchronizable than this other higher order Kuramoto model. Yes, please. Mhm. Yeah. Yeah, 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 yeah. Yeah, that's right. Yeah. So, so uh, I don't have an answer. I think we should ask Skardal and Arenas about it. But yeah. So, so let's say that. So in the Kuramoto, I have no idea if this makes sense or not. So I would leave. But yeah, that's right. That's right. But this might not in the Kuramoto model, but maybe in so having this type of structure makes sense in some control application. It might make sense, but no, for the Kuramoto, I don't know. I'm just I'm just so the idea here is just to show you that there are two different Kuramoto models, and that the synchronizability performance as we were trying to define them are look quite different and different from the also from the pairwise one. So is this just by chance, or is this something? Is there something more? Yeah, yeah, absolutely. Yeah, yeah, yeah. Yeah, okay, yeah, yeah. Here the let's say the focus was not on the feasibility of the model. Now when so what we want to do then is to compute, first of all, to find an now the first thing that we need to do, we need to find a general way to find an estimate of this convergence bound. So without simulating the system. So the thing is, the crucial bit is we don't want to simulate the system. Okay. Uh, and so doing what we obtained is this complicated expression, if you want, but beyond this, the complexity. So here you can highlight basically uh, some the detrimental effects related to the individual, to possible instabilities, individual dynamics, and to parameter mismatch, and then you have a beneficial effect which is potentially related to coupling if coupling helps. And what we observed is that both for, first of all, we need a bound that is reliable, an estimation that is reliable if you want to rely, if you want to build our synchronizability index on that. And so the first thing that we checked is how it correlates with the actual bound coming from simulation. We did it for the Kuramoto model, we did it for coupled Rosler oscillation, and we got a fairly good correlation. So what we did then was uh, to define synchronizability as the inverse of this convergence bound. So the smaller is this convergence bound, the better is synchronizability for the network. And so now we would like to check whether this thing that we observed with the source hypergraphs and sink hypergraphs is actually something that is there, or was just an instance for that simulation on the Kuramoto model. And so what we did, we compared three different hypergraph structures, so with only sink hyperedges, like the Kuramoto model that Stefano introduced, the source hypergraphs like the other Kuramoto model, and a mixture of the two, where you can have both source and both sink hyperedges. We compared it with pairwise interaction also, so with digraphs as well. So what we, and now the thing is, how do you compare? So you need to compare them fixing something that make the comparison fair. So we did it in two manners. So in the first case, we fix the overall degree. So the total number, let's say, of tails and heads in outgoing and incoming at each node. And in this, with this comparison, you find first of all that D-graphs always synchronize better than hypergraphs, but the hypergraphs are not all equivalent. So it looks actually that what we observed in that instance is actually true. So when you have sync hypergraphs synchronize better than random hypergraphs or than source hypergraphs. Of course, we are focusing just on triadic interaction. This is just to mention. But so are D graphs always better than hypergraphs for synchronizability? Well, it depends on how you compare them. Because, for instance, when you fix the overall degree, what is going to happen is that you are going to have more edges compared to the hyper edges, because to get the same degree when you have hyper edges, you need less hyper edges. So instead, another thing that you can do is to fix the cardinality of the hyper edge set. When you do that, you find much more comparable synchronizability result between D graphs and hypergraphs, and in particular, interestingly, you find that there is no statistical difference between the synchronizability of D graphs and the synchronizability of sync hypergraphs, which still outperform all the other types of hypergraphs. So, concluding, so my idea was to share with you this need to further investigate the role of the hypergraph topology on synchronizability, on our ability to synchronize the network. It's actually an open problem. This is just, let's say, a first step. So first observation that I found interesting, but there is much more to be done in this respect. We need to study all the other possible interacting structures. Of course, structure that makes sense. And but other questions that are open, well, of course, a possibility, something that Stefano was mentioning last week, is when you have behaviors which are not synchronization. So if you want to enforce other type of behaviors, so how does this play out when you need to enforce other types of behavior which are not synchronization? Because synchronization is just one possible collective behavior. Then you have other type of behaviors that you can enforce in the network. And finally, as Hernan and Stefano were discussing yesterday, so what happens when you don't have diffusive interaction, or diffusive-like interaction, you don't even have synchronization, then the coupling protocol is synchronization invasive, so it doesn't disappear when the nodes synchronize. So how do you deal with those cases? So these are all open problems, and I think there's a lot of room to work in this area. Thank you.
We have time for questions. Anybody? Yes.
Here you are treating non-identical systems.
Yes.
So of course, it makes the situation slightly more complicated with respect to the master stability function.
Yeah.
Now, in the master stability function, there is a fundamental difference between whether the original node, I mean this isolated node without connections, is chaotic, then the function starts from a positive number, or periodic, and then it starts from 0.
Yeah.
That can have different classes. Here you compared Rössler with Kuramoto. Kuramoto is periodic, and Rössler is chaotic. So does make some difference? Did you find some difference also here? Qualitative difference?
Qualitative difference, no. So the results seems to carry out from one case to the other. What I have to say is that since the nodes are non-identical, then even if you were considering, I don't know, a system which has a stable equilibrium, then still the problem still makes sense. Yes. Because you will have a mismatch in the end due to the mismatches in the if the equilibrium is different from node to node. So this is not the case when the nodes are identical, because when the nodes are identical, then you don't need the coupling to synchronize them. But when the nodes are not identical, so also in case in which the mass stability function is negative at 0, it still makes sense, the problem. Then we didn't consider that case. So, but in general, this is
fixed point.
Yeah, even a fixed point makes sense. You can, but we focus on oscillatory systems. But even with a fixed point, in principle, the problem still is non-trivial.
Clear.
Yeah.
More questions? Hernan?
Yeah, no, talking about the generalization of all this. So how the structure will affect the controllability? Let's say if you have to have a structure, community, or let's say even symmetries. I'm going to talk a little bit about that. But yeah, I wonder what is your point of view as a generalization controlling a network with a very particular structure. I mean, you could take it scale-free, small world, typically, but if it has more, like a strong modularity, a strong symmetries, is that the problem that can be
okay attacked? So but the goal is still to synchronize the entire network. So if the goal is
well, maybe
yeah, depends.
Okay, I let you define your problem. So whatever you could say, that's okay. But in principle, will be even cluster synchronization.
Okay.
But okay, so it's up to you.
Okay, so if you want to synchronize the entire network, then from the point of view of control, one information that we have from the analysis that we made is that you still need to ensure the presence of a spanning tree in the graph. So you still have but this becomes a necessary topological condition. So typically from the topological point of view, you are fine if you have a spanning tree. Then you need to check also some additional conditions, which unfortunately so far are algebraic conditions. So you don't find a graphical condition except in some special cases. So this is already tough for synchronization in the entire network. If you want to talk about controlling cluster synchronization, well, probably you could reformulate this problem and consider probably different bounds at the level of the single communities, and try to so if you accept that you don't have perfect synchronization, but that you have some bounds because of if you don't have special symmetries that guarantee you that the error will be 0, so this approach maybe could be used. He said if you want to use symmetries, well, you need to design a control input that is not going to destroy such symmetry. So you will need to take into account that. I don't have any results or any. Just thinking with you right now. Yeah.
There is a recent paper by Mattia Frasca, the group of Catania and myself, in which we made exactly this, but for identical systems. For identical system, the problem is fully solved in the sense that you can take any network, design as you wish the way this network has to function in parallel. So you can create cluster where they are not present in their symmetric properties by just a controller, external controller, the paper I sent you this morning. You can change the stability properties of existing clusters, that is, clusters that are unstable, you will never see, you want them to be stable, you can do. And you can also change the sequence in which cluster appear in the sequence. So if you want one cluster to appear before the other, so practically if you are, again, synchronization on invasive and identical system, practically you can take any network you want and make this network to work in parallel as you wish. The problem is that when you destroy these two conditions, and then you have to go through these things one side and the other side even worse.
Yeah.
The problem is that we don't know how much of these generic results can be inferred for a generic case as you are thinking.
More questions? I have one question.
Yeah.
So this is about that point which Stefano mentioned the other day, that synchronization is not always what you are going to study. So do you have any intuition or preliminary ideas that you can say about this case? For example, the kinds of networks that I have been studying with real data are brain networks and not necessarily connected to synchronization. So it'd be interesting to have some intuition about the extension or generalization of these results to non-synchronization.
Well, first of all, you need to change the control input. So, here you are considering as a reference a node which is identical to the other, or at least except for some parameters at most, and then you want to drive the system towards that trajectory. Now, if instead you have other goals, which is not to synchronize the network, maybe you want to one area, I don't know, one area of the brain to behave in some way, and one other area in another way, then you need to differentiate the type of input that you are sending, and so you need to redefine, to redefine and redesign the control input, basically. So from scratch, I would say. I would start from scratch.
Thank you. More questions?
Hi, thank you for your presentation. I have a doubt about the implementability of this method to experimental data, because in my work, for instance, I don't use the Kuramoto or any other model. I just take experimentally the data of each electrode and try to synchronize them. And so we can also use this application with the problem. There is also the problem of invasive interactions in these cases of experimental data.
So the thing is, first of all, if you have experimental data, the first thing that you need to ask yourself, do I have also the model? It's just some data that I'm collecting somehow, but I don't know where they come from? Or do I know the model where the data come from? If you know the model, then you replace, instead of the Kuramoto model, instead of the Roser system, you use your model, you use your dynamics, and then you can apply this method as it is, as it stands. Otherwise, the other possibility is that you don't have the data. You don't have the model. So how do you deal in that case? Well, first, it's a more complicated problem, because in that case you have a time series, and in principle you don't even know if you are having or you are not having higher order interaction in that time series. You don't know whether you don't know. So ideally, if you can, at least, so you have two ways. So even if you can model and isolate, if you have data on the isolated node, you can first identify the dynamics of the isolated node, so estimate the F in that equation, and then you focus on the coupling and trying to reconstruct somehow the coupling. If not, then it's a really big, huge problem, because so the first thing that you can do, one thing that you could do, and there are people that are doing this, is trying to understand whether you have higher order interaction in the network or not. So just from the time series, you can use tools from information theory, and with these tools from information theory, at least you can get an understanding whether there are higher order interaction. It's worth looking at them, because if not, at least you know that they are not there, and you simplify a bit your problem. But sooner or later, and also it depends very much on the question that you want to answer, because depending on the question, maybe you don't need to reconstruct the network. Maybe you need just some salient feature of the system. Maybe some functional mechanism that you want to reconstruct. So it depends very much on your problem. I cannot give you a general answer.
Okay, yeah? I think it's more for information there. Okay, thank you for
You're welcome.
answer.
We have time for maybe one final question. If no more questions, then let us thank the speaker once again.